I am going to present a joint work done with Professor Mohammed Al-Fattah on mapping neural network inference to heterogeneous hardware platforms. So first, I'd like to start by giving a quick motivation on the setting where our work is situated. So modern data centers are becoming more and more heterogeneous, including different components, so there'll be CPUs, GPUs, and different kinds of ASICs, and not only on the large scale of data centers, but also on the more personal scale of mobile chips and computers, we see an advent in usage of different heterogeneous chips. This can be seen as an answer to the end of linear scaling and the expected end of Moore's law that allowed us to get an exponential increase in compute power per unit of energy throughout time. And while getting additional computer power is becoming more and more difficult, we are developing applications that are more compute heavy, whether it be numerical simulations, 3D graphics with real-time rendering, cryptography, and other kinds of. And the crown jewel in our case is deep neural networks. I don't think I need to convince anyone about the importance of deep learning today, considered one of the most successful optimization routines that has been developed in the last decade, hence the importance of finding efficient deployment schemes for DNNs. And when looking closely at these DNNs, they are also composed of heterogeneous components, whether from linear functions to nonlinear functions, and further structural differences, these may be more suited to be mapped onto different kind of hardware accelerators that can take advantage of their peculiarities. Still, finding a good DNN deployment scheme in a consistent and automatic way is becoming harder due to two main axes of complexity. A qualitative one, which is the irregular structure of modern DNNs. Initially, their topologies of neural networks were fairly straightforward, mainly sequential networks. Example here is AlexNet, which also can think of residual networks. Still, with neural architecture search and randomly wired neural networks, we are seeing the usage of neural cells that are more structurally complex. And on the quantitative side, we see an increase of interest for large models, large language models being a prime example of that. And in this case, the complexity does not come from the neural network structure, which is fairly regular, but from the combinatorial explosions of different possibilities of association between operations and hardware targets. So for these complex workloads, we have no good intuition whether the previous approaches that we used for smaller and simpler DNNs would scale that well. And one of the most successful ways for manipulating these tensor-based objects that are DNNs is via domain-specific languages and their compilers, which allow us to target different hardware backends simultaneously at a high level. So this is only done at an individual basis with a lack of awareness for the whole structure and system that we want to target. And this is exactly where our work is situated. We're trying to propose an automatic scheduling framework for DNN that can be extended easily to domain-specific compilers. So our contributions can be summarized into three main points. First, how to leverage both model and data parallelism for latency and throughput optimization in a consistent manner by proposing a new linear mathematical programming model that allows batching for DNN inference execution. We also introduce an additional splitting heuristic that complements our MLP formulation to schedule complex modular DNNs. This comes with a rigorous theoretical analysis of the lower bound guarantees that we can obtain compared to a theoretical global optima via this heuristic. Now let's take a look at some of the previous work done in that direction, starting from the general scheduling problem, which is considered one of the cornerstone combinatorial optimization problems, appearing in the one of the first compilations of NP complex problem, Karp's seminal list. It has thus benefited from a large body of work investigating different computational complexity of its variants, which can depend on the nature of the machine environment, the presence or not of precedence relationships, and if they exist, how are they encoded? Is it via a planar graph, a modular graph, an in-tree and out-tree? All these have a direct impact on how good a solution for a scheduling instance can be. We can also talk about the presence of communication cost or optimization objective and so on. But when looking at it from a theoretical perspective, the picture is pretty bleak. And For exact solving, we are mainly faced with negative results, impossibility results, due to the strong invariantness of the problem. Still, works by Mnick and Knopf and Kollig try to propose some pseudo-polynomial exact solutions for this problem, focusing each on homogeneous platforms and heterogeneous platforms, but this only target workloads that don't take into account precedency and communication cost within the graph that is scheduled, the DAG that is scheduled. So in this case, approximate solving is the way to go. Here, the picture is a bit more optimistic with the existence of efficient polynomial chain approximation schemes, but we are still faced with a lot of approximability results. We should still mention that there have been some recent breakthrough in this direction. The main one being, the most recent one being work by Davis and Kollig, giving a logarithmic factor approximation schemes, but this only work on networks that are on platforms that are homogeneous. Just quick recapitulative of what I mentioned before, we are either faced with impossibility results or with partial results. With more general formulations of the problem, an empirical approach is far ahead of our theoretical understanding. And some quick overview of the different heuristic approaches that have been proposed throughout time for scheduling instances are critical path time scheduling approaches that try to look at the longest path within a graph and choreograph the rest of the scheduling around this main critical path. We also should mention the usage of this black box search heuristic that abstracts away the structure of a search problem to only keep it in the form of a optimization of a fitness function, optimization function. And examples of those are evolutionary algorithms, simulating annealing, and so on. And finally, one of the most successful heuristics in terms of quality results efficiency trade-off is the heterogeneous earliest finish time that has been used recently in different scheduling problems. Aliyev and Kollig's work on scheduling workloads on FPGA structures, and Ghannane and Kollig offer a survey where heft is shown to outperform 20 other heuristics for random generated graphs scheduling tasks. And in our approach, we will focus mainly on the approximate solving, and the instance will be as general as possible, being heterogeneous platforms targeted, the presence of communication cost, of memory, footprint, and so on. When looking more closely at general software partitioning, heterogeneous scheduling for general purpose compilation can be split into two main axes, one that is done at static time and the other done at dynamic time. So for the former, it relies mainly on partial approaches targeting either specific workloads or specific hardware architectures. And for the latter, it's mainly reliant on some insight of statistical distribution of the workload and taking our decisions based on that. Compared to that, we are performed at static time, like the former approach, but these approaches are tailored for deep learning architecture specifically, where we are using a coarse graph level structure that abstracts this DNN. And now looking closely at what interests us, which is DNN scheduling at inference time, here I propose just a quick overview of the different approaches that have been done in this direction. Large body of work exists here, but Chen Kollig proposed an exact solution by focusing only on the dense-net architecture, giving a pseudo-polynomial time exact solution via some dynamic programming approach. Still, this cannot be extended to other architectures where their main insight, which is defining redundant edges, is hard to generalize for other structures in an efficient manner. Duet is a work that works by coarsening our graph at a really high level, partitioning the graph onto different modules, and placing the critical path of this coarsened graph on the fastest device and organizing the rest of the solution around this in a post-processing manner. Finally, Serenity works on scheduling irregularly wired neural networks, proposing one of the first principled work to do that, but the objective differs from us, which is, in their case, optimizing the memory footprint. Here is a quick summary of what I mentioned. For the first work is too narrow focused, work specifically for DenseNet. Second, it doesn't exploit model parallelism by doing this coarsening approach and work mainly around critical path. And finally, one of the first work on NAS networks, offering a principled endeavor, is working for a different objective than us. I would also like to mention another line of work that exists for DNN scheduling, which is the deployment of large language models on distributed systems, and more generally, large models. These suffer from a consequent memory constraints. The model cannot fit on a single processor anymore, or even a single compute node. And despite novelty of this new interest on large models, we can see different works working in this direction. And these all are relying mainly on handcrafted strategies, whether it be optimizing some specific transformer kernels, or using mainly pipelining or some set of best practices. We're trying to propose a first overview of what would look like a principled approach to leverage model parallelism for these large models. Now, I'll just describe the framework that we have proposed, which is DiviML. Oh, its overall pipeline can be summarized in this figure. We're starting from a DNN encoded as a torch FX graph. We go through an optional clustering step that works in a pattern matching basis, trying to coarsen our graph slightly to make it more easy to manipulate. A prime example of that is folding redos and batch norms into convolution operations. Then our mapper is also fed a system description of the hardware platform that you are targeting in the form of a JSON file encoding all the main aspects of a hardware structure, the different components, how they are linked, the nature of the links between these components. And with these, our mapper proposes a schedule that optimizes for a given objective function, which is then fed to the backend compilers to generate the appropriate binaries. Now to look in more details of what we mean by a scheduling instance. So let GVE be a DAG encoding our DNN application, V being the set of tasks, E denoting the set of edges representing data precedence relationships. And for a given hardware system description and the appropriate objective functions that you are targeting, in our case, it's either latency or throughput, we are outputting a mapping schedule of J on H optimizing for the given optimization function. Also, what we mean exactly by latency objective and throughput objective. In the latency, it's the classical case where we are fed a single inference input, and that we are trying to process as fast as possible in our schedule. In the throughput objective, it's the batched execution case where we are faced with multiple inputs to process as fast as possible. Once again, with the possibility of splitting these batches across devices that can be processed simultaneously, here, as can be shown in this figure here. Let's look at an example of a schedule for a single inception module that has been mapped and scheduled on an example, a heterogeneous platform composed of one CPU and two GPUs. Examples of leveraging data parallelism can be seen in operation 0 that has been processed simultaneously on the T4 and on the A100, and of model parallelism, the processing of the operation 2 and operation 6 in parallel. As I mentioned before, the algorithmic solution adopted is an MLP model. These can be explained by two reasons. First, MLP models offer a flexible and expressive framework to work with when encoding a combinatorial optimization problem, allowing us to add incrementally additional constraints and see the impact of each of those. And also with the advent of efficient modern solvers, these can match some problem-specific algorithms on hard NP complete problems. Example of these successes can be seen as in the vertex coloring case, or even on the traveling salesman case, and we're trying to emulate that for our scheduling problems. But this comes in the cost of having to do some linearization of constraints when trying to encode by intuition what we can see in the schedule instance. These do not directly translate into a set of linear inequalities, hence the need of doing some linearization. An example of these techniques is the Big M method that we have used extensively for the expression of batching constraints. And doing that can result in bloating the size of our model, hence the additional lead of doing some optimization work on the model to allow it to scale for larger sizes of instances. This scalability of MLP is tried to achieve by exploiting some graph properties that we can find in our specific workloads that are DNNs. And the main one tackled in this work is the usage of modularity within a DNN. We have done this at both a macro level and macro level. Macro level, we mean by that doing an optimization at the stage of the MLP model in itself by reducing the redundancy of constraints. Example, of removing non-overlap constraints, these can be encoded with dependency constraints only. On the macro level, this is seen as doing a divide and conquer approach on the whole graph before encoding it as an MLP. This is our specific heuristic, the MLP split. So first, what do I mean by a modularity within a graph? This is the presence of highly connected clusters within a DNN that are communicating through few channels. This is present in a lot of popular DNN architectures, the inception-based networks, transformer-based networks, and so on. And the high-level approach, high-level idea is for our scheduler to partition the global problem, the global scaling problem, into independent solved problems that we can solve independently and combine in some manner to obtain a solution for the global instance. Still, when combining them, a legitimate question is to ask, how much do we lose in terms of quality of results? So the answer is twofold. We distinguish between the single channel and the multi-channel case. In the single channel, we managed to reach an exact solution, whereas in the multi-channel case, we propose an approximate solving scheme that also comes with a lower bound that gives a guarantee on how far we are from a theoretical optima. So starting with the single channel modularity, identifying modules is fairly straightforward. And our solving is reliant on a dynamic programming that takes advantage of the global ordering that we can establish between the scaling time of each of these modules due to the linear sequential ordering of a DNN when the different modules communicate through a single channel. Further details on the dynamic programming formulation can be found on the paper. But for the multi-channel case, even identifying modules is becoming harder, doing this either through some multi-level recursioning with tools like Metis, or by finding the KH connected components, which works particularly well for irregular graphs. Still, with the existence of multiple communication channels, we lose that monotone structure, this global ordering that we had for the single channel case, hence losing also the optimality guarantee. So I want to quantify how much of a trade-off we have between the quality of our solution and the efficiency obtained with a splitting heuristic. This comes in the form of a lower bound optimality guarantee. So to define that, first, I'd like to introduce some notations, which is the dependency graph, a precedency graph of a given node in our graph based on a subgraph. So the dependency of U in a graph based on T is the set of vertices in T for which there is a patch from U to V. And we define the converse notion with the precedency where now it's the patch from V to U. This can be further seen more clearly in the figure below. Also, so for a GVE DAG, which can be split into different modules MI, we define GS being the suffix graph, which starts at the module number S until the end of our graph. It's a subgraph of J. And recursively is how we want to proceed to define our lower bound. So for that, I define by IT the set of inputs of G2, the suffix graph starting at the second module, and OT being the set of outputs of M1. And we managed to obtain a lower bound on the global solution of V based on solution on optimal solutions of M1, optimal solution of J2, and optimal solutions of the dependency graphs and precedency graphs of the inputs and outputs. And we can see this can lead to a global lower bound of up to V when repeating this recursively on opt of G2 and on the dependency precedency graphs, where in the end we'll only need to compute optimal solutions for modules or for subgraph of modules. Sketchable proof and further details can also now be found on the paper. So yeah, like I mentioned before, we apply this lemma recursively to obtain the lower bound on the whole graph. while being also efficient, since we only saw 4 modules or subgraph modules, and it is also tight. Tightness can be reached in the case where we only have a single channel trivially, but also in cases when you have a lot of communication channels, this also leads to a tight result. And this also gives us an intuition on the more communication we have between modules, the closer we are to our optima, both for our splitting heuristic. Still, what I expressed before only works directly for the latency case. So what happened in the throughput optimization with batched input, this can be immediately extended to batched case with the reasoning on the smallest possible input on all given hardware platforms. But we can still do better when starting with a global input of size L. After scheduling the B copies on the first module, we still need to schedule L minus B plus 1 copies on the dependency graph of the inputs of G2. And this allows trickling down the whole input throughout our graph in obtaining a better lower bound than just proceeding naively with the smallest possible input. Now, just take an overview of the experimental setup used to evaluate our platform and some of the results obtained. So our evaluation is done on both regular and irregular networks. For the latter, we took 6 samples with 32 nodes per module each, sampled from different random graph generators, like Erdo3, Watts and Barbasi Albert. The heterogeneous platform sample that we have used is one with 1 CPU and 2 different GPUs, and we are evaluating for both latency and throughput, comparing against classical scheduling heuristics and black box heuristic. Now, in the latency case, for regular networks sampled from Cherish Vision, we only see a clear advantage with networks with high parallelism like Ghannane Inception, and with other heuristics also performing quite well. For more complex networks, we clearly see the advantage of MLP compared to other heuristics into the single device case. So compared to other heuristics, we see an overall 20% best over others. And this evaluation on randomly wired networks is only done on a single module. So if we want to extend that to networks, randomly wired networks with multiple modules, we need to define how these modules are connected. For that, we introduce 2 different kinds of randomly wired networks, single strongly dependent and weakly dependent networks. The details of their definitions are further explicit in the paper, but just taking a quick overview of the results here. MLP converges reaches the optimal solution, whereas MLP split is a close second, outperforming all other heuristics and being closer to the optima for this strongly dependent case, where we have a larger number of communications between the different modules, as I've expressed earlier in the intuition of the lower bounds that we had. Whereas in the weakly dependent case, the lower bound is closer to the optima, since it matches more closely the dependency dependency and precedency subsets are closer to what the MLP does. However, someone may wonder why we need to compute a lower bound when our MLP is convergent in the latency case, where we can just compare our split to the MLP to see how close we are to the optima. When the answer comes in form of this table, where MLP can be a lot slower than MLP split, up to 390x factor of speed, and having a fast and efficient way to compute a lower bound on the theoretical optima allows us to evaluate how good our MLP split solution is without needing to go from this time-consuming step that is finding the global optimal solution. Now, on the throughput scenario, we are starting with a patched input B that is decomposable into a quarter, a half, and 3 quarters. And now we can take advantage of both parallelism at the scale of the model, but also data parallelism with simultaneous execution of batch of inputs. Now, even for regular networks, MLP doesn't converge anymore for a 2-hour deadline, so giving an advantage of MLP split in this case, even for regular networks that have high model parallelism like Ghannane Inception. And as before, MLP outperforms other heuristic for the single module randomly wired networks. In the multi-module randomly wired neural network, MLP is not the best solution anymore. It's not even the second best in some cases with multiple channels, and MLP split is the way to go to obtain an efficient scheme for mapping this multi-channel, multi-module randomly wired networks in throughput optimization objective. Now take a look at some case study that we have implemented for large language models on distributed heterogeneous nodes. So as I mentioned before, the current large model cannot fit on a single device anymore. And these transform and they exhibit high regularity. Example of this is the transformer-based models. And the complexity comes from the large search space, the combinatorial explosion of possibilities of hardware, device, and operation mapping options. So in our case, we will consider GPT-3 on this simple distributed platform consisting of multiple nodes, each 6 nodes, each composed of a CPU and multiple GPUs. And I'd like to emphasize that these are only early results where evaluation is done on a single decoding step of the LLM. The main objective is to show the flexibility of our schedule that can scale to larger models with large heterogeneous hardware platforms by exploiting opportunities for model parallelism. And this, the main idea between by doing that to allow our solution to scale is doing some pruning of our search space via symmetry breaking. In the different evaluations ways we'll implement, there is a single node and multi-node approach. So the single node is seen as a competitive baseline where we schedule 1/6 of our GPT-3 graph on a single node, then replicate it on all other nodes. This tries to emulate how an efficient manually partitioning LLM is done in practice, whereas the multi-node is what we are trying to propose to show how targeting the entire compute system by our solver can be done by symmetry breaking. So first, what I mean by symmetry breaking is introducing some additional constraints from MLP formulation to enforce an ordering on variables for identical devices within a node or between nodes, and to prune away equivalent solutions that are done just by swapping operation to device mappings that result in exactly the same solution. Still, if doing this carelessly, can result in some risk of premature convergence, where these additional constraints can work against the heuristics taken by the solver and resulting in a worse solution for the same time span of solving. We thus can ask what is the best choice to have a implementation of symmetry breaking without a high risk of premature convergence, whether it be the number of batches that have been mapped on a device or the number of tasks that have been mapped on the time utilization of this device. Now we'll take a look at some of the results we obtained. So what we can look, some insights that can be seen in this figure is that sometimes no symmetry for the MALP, sometimes all symmetries for the MLP can result in a worse solution than MLP split for a single node compared to multi-node when choosing the worst symmetry breaking criterion. In this case, is number of batches. Number of tasks, number of times allows an increase in solution quality. And also, which symmetry is considered can also have an impact on how good our solution is, whether it be intra-node with devices within the same node or intra-node devices between nodes. So, quick summary of what this results is that we managed to achieve up to 31% gain over baseline scheduling, so MALP in a single node, and 10% over single node MALP split. Also, this choice of symmetry breaking criterion is important because choosing it carelessly can result in a worse solution than MALP split with no symmetry breaking. And finally, the choice of symmetries can have different impact. Since we have higher intra-node symmetries, these result logically in better performance when considered independently. So just to conclude, what we try to propose is an MALP-based general scheduler that is DNN-centric, that relies on properties that we can find on DNN workloads, which is modularity, the possibility of batched execution, and data model parallelism. We also rely on this splitting heuristic, which comes with provable guarantees, being both efficient and scalable. And finally, we show the flexible formulation of our framework via the case study to tackle diverse scenarios, in this case, which is memory constraints for large language models through symmetry breaking. Thank you.